The passenger electric vehicle market is accelerating rapidly. Automakers are completely overhauling vehicle design today, moving towards software-defined architectures, where fewer mechanical dependencies allow for centralized software control. We see this momentum clearly in commercial autonomous fleets. Operating on predictable, defined urban loops, the driverless robotaxis scaling up in major cities today are built almost exclusively on battery electric platforms. This data table shows the financial catalyst driving that adoption. Over the last decade, battery pack prices have fallen by 75%, while energy density has increased by 60%, steadily closing the price gap with internal combustion engines. For short distances, highly predictable routes, and lightweight chassis, the market has delivered a clear verdict. In the urban passenger space, the lithium-ion battery has won. As batteries get cheaper, a dangerous assumption has taken root among the public and some investors. The belief that we can simply scale up this exact same technology to electrify the entire global supply chain. Transport is not a single, uniform industry. It is a wide spectrum of vastly different operational profiles, and at the heavier ends of that spectrum, it is governed by uncompromising laws of physics. Successfully navigating this energy transition requires abandoning the one-size-fits-all electrification narrative. Passenger cars spend most of their lives parked. Heavy industrial machines are continuous-duty energy conversion tools. Applying passenger car logic to heavy supply chains will guarantee operational failure and burn massive amounts of capital. To see where the battery thesis first begins to encounter friction, we have to look just outside the urban core, at intercity buses and heavy logistics trucking. In specific, localized use cases, heavy vehicles work well. Battery electric technologies for urban and regional buses have achieved total cost of ownership parity with diesel, making them a highly cost-effective option for municipal transit. Long-haul trucking faces a different reality. The sheer physical weight of the battery packs required for cross-country range directly cannibalizes the truck's profitable payload capacity. Moving those heavy vehicles requires high-capacity rapid charging on highways, which demands robust grid infrastructure. For the charging operators, securing that grid capacity involves exorbitant upfront costs that often exceed the price of the charging equipment itself. While long-haul battery trucking is technically feasible, these infrastructure costs create immense financial friction. This is especially true for the countless small and medium enterprises that actually dominate the highly fragmented global freight sector. Moving further off-grid, we reach the extreme edge of the perimeter. A Caterpillar 793 mining haul truck carries roughly 226 tons of material. Vehicles in remote mining and heavy construction operate continuously for 20-plus hours a day. They endure high altitudes, abrasive dust, and heavy vibration, often hundreds of miles from the nearest electrical grid. This graph illustrates how tight energy margins are here. The blue line tracks engine speed during a dumping cycle, and the green line maps fuel consumption. A slight throttle increase from 1500 to 1900 RPM causes fuel burn to nearly double instantly. In agriculture, constraints shift to seasonal utilization.
A combine harvester requires an enormous continuous power draw for 15 to 20 hours a day, but operates in highly compressed 3-week harvest windows, far from any charging network. Powering these machines requires alternative engineering. Manufacturers are developing tethered electric systems for specific mine sites, investing heavily in hydrogen fuel cells, and designing new chassis that are entirely agnostic to their powertrain. Their current diesel consumption would exhaust any modern EV battery within minutes. Standard passenger battery logic completely collapses under the extreme physics of industrial duty cycles. Past the shoreline, we hit the final frontier of global transport, transoceanic shipping, and medium to long-haul aviation. Here, the battery question is closed. Pushing thousands of tons of steel across an ocean, or lifting a commercial airliner into the sky, requires so much stored energy that relying on batteries is purely impossible due to their low energy density and immense weight. Replacing diesel in maritime shipping requires energy-dense liquid or gaseous fuels. The live competition in this sector is currently focused on scaling up production of green ammonia and e-methanol to power these massive vessels. In aviation, sustainable aviation fuel, or SAF, is the only viable alternative. It is a drop-in chemical substitute that works safely with existing jet engines, but it currently suffers from severe supply bottlenecks and costs 2 to 5 times more than conventional kerosene. For the sky and the sea, the central investment bottleneck is no longer about designing better electric motors. It is about financing and scaling entirely new global chemical supply chains. There is one notable exception where electrification is currently advancing regardless of heavyweight and grid constraints: military ground vehicles. Here, the requirements are not strictly about commercial economics or emissions reduction. Electric motors provide distinct, lethal tactical advantages. They offer completely silent mobility for reconnaissance and eliminate the thermal signatures of running diesel engines, making soldiers harder to track with infrared targeting. In a defense context, electric vehicles are weaponized to serve as silent, highly mobile power distribution hubs for complex battlefield electronics and sensor arrays. A complete map of the transport economy has taken shape. We will rely on solid batteries for the urban core, hybrid systems for the industrial perimeter, and complex fluid chemistries for the ocean and sky. For executives and capital allocators, this reality demands a highly disciplined strategy. Betting a company's entire product portfolio on a single technological pathway invites severe corporate risk. We are already seeing heavy operators manage this uncertainty. Major maritime fleets are intentionally ordering dual-fuel vessels to ensure they can burn multiple chemistries over a ship's 30-year lifespan. The electrification of passenger cars and light commercial transit is a verified, unstoppable commercial reality. But the long-term competitive advantage will not belong to organizations that try to force a single battery chemistry onto the entire world. It will belong to those who accurately measure the physics of their industry and strategically master a diverse portfolio of competing energy technologies.